So maybe we should get started. So hello, everyone. Welcome to today's session of the Imagine seminar. And I will be the host today, and it's a great pleasure to be the host today because Elie Bretin is talking. Elie actually was my student at the University of Grenoble, so I'm happy that to see that he made so much progress that now he's speaking to an international audience. And Elie got his PhD in 2009, if I'm not mistaken, and then afterwards was a postdoc for a couple of years at École Polytechnique. And then he got a position as maître de conférence at the INSA of Lyon. It's an engineering school, but his research is attached to the Institut Camille Jourdan. And Elie's topics of interest include the numerical approximation of the evolution of interfaces, and also inverse problems, and particularly elastography and with applications to medical imaging. And so today, Elie will talk to us about mean curvature flow, neural networks, and their applications. And Elie, the floor is yours. Welcome to the seminar.
Okay, thank you very much for the introduction. And I'd like to first thank the organizer for the invitation and to give me the opportunity to talk about a recent work we did with Roland Denis, Simon Masnou, and Gary Terry about mean curvature flow and especially the mean curvature flow in the case of non-orientable interfaces. And we try to apply the technique of neural network to obtain very simple and nice scheme. So, in fact, if you consider a lot of application like material science, physics, biology, image processing, and data science requires a minimization of surface energy, like perimeters, Wilmore energy or anisotropic perimeter. I give you some free picture of a problem we are interesting some time ago. The first one is an example of a soap bubble, which can be obtained, for example, by minimizing a multiface perimeter with additional constraints. The second one is an example of a red cell where the shape is obtained by minimizing the Wilmore energy with a constraint on the volume and area of the set. And the last example is a nanowire. In recent project, we proposed some phase field modelization of nanowire, and here at this scale, it was necessary to introduce some anisotropic perimeter to take into account some privileged direction. So I want to explain here I want to speak about phase field approximation in the case where it's easy to approximate interfaces when she's oriented, and show after why it's more complicated for non-orientable interfaces. About application, for instance, in image processing, we can consider a simple example of image segmentation where you want to find a partition with weight which are very close to a picture. And to obtain this kind of reconstruction, segmentation, we can, for example, minimize a discrepancy functional with an additional regression term, which consists to penalize the length of the perimeter of each phases. And so we'll see that the phase field method is very good tools to obtain an approximation of this solution. Another example of application which we focus recently is, for example, 3D segmentation reconstruction for magnetic resonance imaging. If you consider this kind of data, it should be interesting to have a segmentation of the volume, but we have only information of each slice, which is 2D segmentation. And all the problem should be to obtain 3D segmentation, and which succeed to connect the different states between slices. And it can be very difficult because the topology as in this example where you want to reconstruct the white matter of the brain, the topology is more complex, and you need to connect thin sets between filaments. And we proposed recently to minimize some geometric surface energy, like perimeter or Wilmer energy, under exclusion and inclusion constraints, which satisfies the constraint of each slice. I give here an example in 2D, where, in fact, I give you in the middle picture the reconstruction if I want to minimize the perimeter, and the second reconstruction is obtained with a minimization of the Wilmer. So you see that the Wilmer give some smooth reconstruction, more natural. Okay. So if now I focus only on the perimeter, if I want to minimize the perimeter, I can consider the L2 gradient flow of the perimeter, which also can be obtained by the total variation of the characteristic set function of the set omega. And this L2 gradient flow consists to evolve an interface, oriented interfaces, with a normal velocity given by the mean curvature. So this is an example in 3D where you can observe the singularity at finite time and the changement of topology, which is typically the case in 3D. So there is a lot of numerical method to do this, parametric approach, level set. Here we focus only on the phase field method, which is a variational method which consists to approximate, in fact, the perimeter with an energy in the sense of the gamma convergence. And this approximation is given by the cannular energy with where epsilon is a small parameter and W is a double well potential with vanish and 0 and 1. We have a result of gamma convergence of P epsilon to the perimeter in L1, and it is proved by Modica Mortella. In fact, if I consider, if I come back to the mean curvature flow, and if I take an example in 2D of mean curvature flow, the interest of the phase method is that if I consider the Allen-Cahn equation, which can be obtained by the L2 gradient flow of the perimeter, the cannular energy, and if you make a resolution of the Allen-Cahn equation, we can observe in fact, a kind of characteristic function of a set which evolve with a law which looks like to a mean curvature flow. So this is a good, very good phase field approximation for the mean curvature flow of oriented interfaces. Here the characteristic set is smooth with a size of which the size of the smooth is given by is linked to the epsilon parameter. More precisely, we have some result about this approximation, and which is of order 2 in epsilon, which means that U epsilon, in fact, can be identified by asymptotic expansion to a profile Q, which depends of the double well potential applied to the distance of a set omega epsilon under epsilon, plus an error in epsilon square, and where the set omega epsilon evolve in time following an approximation of the mean curvature with an error in epsilon square. This means that if you want to obtain an approximation of mean curvature flow, it's just sufficient to solve this Allen-Cahn equation, and you obtain the position of the interface with an error in epsilon square. The phase field method is very a nice tool because this equation, the MT equation, is a reaction diffusion equation with an homogeneous differential operator, which is and a nonlinear operator, but for which we have a very simple and efficient numerical scheme. For example, here I can consider an implicit treatment of the Laplacian and an explicit treatment of the double well potential. And if I take alpha sufficiently large, I can prove that the total scheme is unconditionally stable in the sense that it decreases the cannular energy. And this kind of scheme can be implemented, for instance, in MATLAB using only a fast Fourier transform to to compute, to treat implicitly the Laplacian. So it's very simple scheme and very simple to obtain this kind of evolution. A last point is that the phase field approach can be adapted to many contexts, in particular volume constraint, inclusion-exclusion zone, multiphase framework, approximation, and various flow and isotropic curvature, Wilmore, and surface diffusion. And this is a lot of my work in my research about all these constraints and this kind of flow. If I come back to the segmentation model, in fact, I want to find a partition, and then we can simply introduce an approximation in the source of the gamma convergence of this segmentation model, which consists simply to introduce a vector where each component is associated to one phasis, omega y, and just to approximate the perimeter of omega y by the cannular energy applied to the IM component of U. And the constraints of partition can be implemented in phase field approximation by a simply constraint, which means that the sum of each component of U equal to 1. So we have very simple scheme Is for the Allen-Cahn equation to minimize G epsilon if you consider it's L2 gradient flow. And this is what you obtain, for instance, where here I take an image of which come from from resonance magnetic imaging, and we consider only 4 phases, and I just modify the coefficient beta, which corresponds to the regulation term parameters. Sorry, and we see that if we grow up beta, we can obtain a partition where the length of the perimeter of the partition diminish. Okay, if I come back to the example of minimizing the Wilmore energy under inclusion constraint, I can do exactly the same. And for instance, there is some classical Wilmore approximation, which consists to integrate the right side of the Allen-Cahn equation square. And the advantage of the phase field is that we know by asymptotic expansion the profile of U, and so you can adapt the inclusion-exclusion constraint by simply inequality on U, where in fact this term is the phase field representation of the set omega 1, and here's the phase field representation of the set omega 2. And this is in certain sense smooth inequality, and so you can easily minimize this kind of energy, like for the Allen-Cahn and the cannular energy. Sorry, and we can treat this kind of constraint with projection. This is what you obtain, for example, with a real image of the brain with 2 phases. And if you want to have some detail, we can see your paper we made recently about volume reconstruction from slice with François Derens and Simon Maston. Okay, so all the application I mentioned is consider some oriented interfaces, but in other application we can have non-orientable interface. It is the case if you want to denoising an image I by minimizing the Mumford functional. The idea here is to introduce a denoise version of I by minimizing a discrepancy functional, but we want to smooth the solution U everywhere except to a set of K, which means that we allow you to have some jump and singularity on a set K, which can be optimized, and we penalize also the length of K. So to do this, we see that we cannot apply the cannular energy to approximate K because K here is not the boundary of a set. So there is some phase field approximation, which is a little bit different. the sense that we don't approximate the length of K by the Camille, but we introduce Ambrosio-Tortorelli approximation, where we simply replace the double well potential by a potential with only one wells in one. I give you here some picture of this approximation, where you see that phi is equal to 1 everywhere and will vanish on an approximation, a diffuse version of the set K. In fact, the problem is to minimize this kind of energy. We have a lot of problems. I don't understand how you can obtain easily a minimizer. And for me, the things are not also simple than using the Camille energy. To illustrate this point, we consider two other applications. The Steiner problem, where the problem consists to find from a given collection of points, x1, xn, to find a compact connected set K, which contains all the points and we have a minimal length. Typically, this is an example of Steiner solution if you consider four points. And you can see that the set K is also not oriented and have also singularity in the sense that we can observe some triple junction. So this problem can be obtained by minimizing the perimeter of a non-oriented set K with inclusion constraints. So if I have some numerical method to do this, I can easily obtain a solution of the Steiner problem. It is exactly the same for the Plateau problem, where is an equivalent in 3D, where the problem consists to find minimal surfaces, which boundary is given by a closed curve gamma. And here you can also see that we can observe some minimal surfaces we have which are not oriented, and we have also a triple line singularity. So in recent project in France, in Geometria, in ANR Geometria, some different model was proposed to tackle the problem of the Steiner problem in dimension 2. And for instance, Mathieu Bonivar, Antoine Lemelan, and Filippo Sant'Ambrogio proposed to couple an Ambrosio-Tortorelli functional with a geodesic term, which penalize, in fact, the distance between each point with the weight given by U. This problem, this fast field model, gamma converge to the Steiner problem, in the sense that if the coefficient lambda epsilon goes to 0, they prove with a very technical result that this term should converge to the distance of a set K, where K is path connected to whole Xe, and where the Ambrosio-Tortorelli functional, in fact, measures the length of K. So to obtain the solution of the Steiner problem, with this gamma convergence result, we can minimize this kind of functional. This is what we want to do. However, in practice, there is many numerical difficulties to do this. And this is our contribution about this work in the recent work with Mathieu Bonivar and Antoine Lemelan. It is very difficult because if I want to minimize F epsilon, we can consider its L2 gradient flow. And if I consider L2 gradient flow, I need to derive this geodesic term with respect to its metric U. And the problem is that if I, for example, consider only 2 points with U equal to 1, this differentiation should be a Dirac mass on the segment which connect these 2 points. If I do with a numerical method, for instance, based on the Hamilton-Jacobi equation, and if the point is in the same line of pixel, we obtain a Dirac mass. But if you do exactly the same where the point is located in an oblique direction, we obtain a very smooth approximation of the Dirac mass. And this explains why, in practice, it's very difficult to obtain an efficient solution of the Steiner problem with a minimization of epsilon. So we try to consider a technique where we don't need to difference this term, and this can be done by a relaxation viewpoint where you introduce a new variable, which is all the paths which connect all the coupled points, x0 to all xi. And if you do this, you need to alternate a minimization of Ambrosio-Tortori functional with this point with a computation of geodesic geodesic with respect to the metric Q. But the advantage is that it does not require only computation of the definition of the metric. The second problem is that if you consider the solution is not so smooth and the solution U is not Lipschitz. And so from a discretization point of view, you can have some surprise if you consider two different mesh, for instance, which conduce to two different solutions. And so to resolve this problem, we also improve the regularity by replacing the nabla of U by its Laplacian. And the last point is that if you consider the geodesic term, in fact, the geodesic term, if the past is fixed, it can be viewed as the integral of omega of a Dirac mass on gamma I multiplied by this term, which shows that its L2 gradient flow conduces to a kind of Allen-Cahn equation plus a penalized term, which is very singular. And in the phase field approximation, in certain sense, all the size, the minimum size is given by epsilon, and you see that we can have some numerical issue for the resolution of this kind of equation if you are here a Dirac mass where on gamma I. And so a natural strategy consists to smooth this term by a convolution kernel of size epsilon alpha. So if you do all this improvement of the model, can I obtain some solution? This is an example of solution, but in fact, the resolution is not so fast. So to obtain a good approximation of the Steiner solution, I need to vary the value of epsilon along the iteration. This is another example with 5 points. The interest of the introduction of the Laplacian instead of the gradient of U is that you can consider also the three-dimensional approximation of Steiner solution, which can be obtained here, like this. And if you consider an initial condition, which is fixed and depend of epsilon, you can see the evolution. And if you reduce the value of epsilon, you see another evolution. And all the question to understand is finally the behavior of the interface should converge when epsilon goes to 0 to the mean curvature flow. And in fact, in practice, it is not the case. And also by using some asymptotic expansion, we can show that the limit law depend on the profile Q, which depend of the Ambrosio-Tortori functional. But in practice, it is not the mean curvature flow. And this is why, in fact, we have a slow convergence to the Steiner solution. So the motivation, in fact, of this work is to understand how you can design a simple numerical scheme to approximate the mean curvature flow of non-orientable interfaces without use a couple of Ambrosio-Tortori functional and additional connectedness constraints. So what is a non-orientable mean curvature flow? It consists to evolve an interface where the normal velocity is still given by the mean curvature, but in which we allow a triple junction which should satisfy a ring angle. And I recall that I don't know any Allen-Cahn approximation to do this. In fact, we propose to try to use neural network to obtain a numerical scheme for an approximation of non-oriented mean curvature flow. So the point is that there is a lot of work which shows that the neural network was very nice tools to approximate PDE. And in general, the idea is to interpret the neural network architecture as a numerical scheme, and to train the neural network, donc optimize its parameter by observing a lot of PDE solution. And then if you can then use the neural network to compute new solution, which the initial condition by simply apply the neural network. And in this strategy, in fact, the neural network, the incoming data for the neural network is the initial condition, the discretization of the spatial variable, and the discretization of the time variable. And to obtain this, we need to have a high-dimensional optimization problem. So the problem about applying this strategy in your case is that you don't have PDE, fast field model, to obtain this kind of evolution. The second point is that we don't know any solution. The only solution we know is the evolution of circle. So we don't have a good database of a PDE solution of what you want to model. So we don't apply this strategy, but your idea is to use a neural network to perform only one evolution time step. The idea is that the neural network can be used to pass to the time n to the time n plus 1. The second point is that you want to use the fact that for the oriented mean curvature flow, we have the Allen-Cahn equation, and you have some very nice scheme to discretize the Allen-Cahn equation, and you want to build some neural network architecture inspired by this scheme, in the sense that we want to have a cost of the scheme which is similar to the resolution of the Allen-Cahn equation. Another point is that we only consider for the learning mean curvature flow of circle in 2 dimensions and sphere and cylinder in 3 dimensions. And to obtain this, we use not the oriented fast field representation, which is given by the profile Q applied to a distance of omega under epsilon, but a non-oriented fast field representation. So all this work has been recently submitted in the preprint you can find in internet with Roland Denis, Simon Maston, and Gary Terrier about learning fast field mean curvature flow with neural network. So the point is, if for instance I just consider the oriented case of mean curvature flow, this is the exact mean curvature flow, and if I want to approximate this exact mean curvature flow, I can solve the Allen-Cahn equation where the initial condition is given by the profile applied to the distance of the initial set omega 0 under epsilon. If I discretize the Allen-Cahn equation, I can obtain an approximation of u epsilon, which gives an approximation of omega of t at the time t with an error in epsilon square. Your idea here is not to solve the Allen-Cahn equation, but to learn to obtain the gradient flow of the exact fast field representation of the mean curvature flow. So we need to want to learn to pass to the solution at the time t to the t to dt with this representation, and not the solution of the Allen-Cahn equation. It's important because in the non-oriented case, we don't have Allen-Cahn equation, but you can just modify the profile to be adapted in the non-oriented case. So the first point is to introduce the exact oriented fast field mean curvature flow, which consists simply to define the function v epsilon applied to which equal to q to the distance of omega t under epsilon. and then also to define the semigroup SQ delta T epsilon, where delta T and epsilon is a numerical parameter which is fixed on during the learning processes, which consists, this semigroup, simply to consider the solution at the time t and to obtain the solution at the time t plus delta t. So we fix delta t and epsilon, and all the problem consists to approximate with a neural network this semigroup by a network S theta. This is a link with the discretization of the Allen-Cahn equation, because if you discretize the Allen-Cahn equation, for example, with an implicit treatment of the Laplacian like the explicit treatment, we obtain a simple scheme which expresses un with un plus 1. And this is what we call the semigroup associated to the Allen-Cahn equation. And so you see that the semigroup associated to the Allen-Cahn equation is very close to the semigroup associated to the fast field representation with Q. And we have an error between the two semigroups in epsilon square only. So the advantage to approximate this semigroup instead of this semigroup is to expect to diminish the fast field error in epsilon square. The other advantage to learn an approximation with a neural network of this semigroup is to compensate the discretization error in delta t and delta x square. If now I want to consider the non-oriented mean curvature flow, the problem is simply to modify the profile Q. And if I want to consider a non-oriented fast field representation, I can simply replace Q by Q prime. And this is, here we use an evolution with Q. Here we use a fast field representation with Q prime. And we see that in this representation, we don't use the orientation of the set omega. And from this representation, we can also introduce a new semigroup named SQ prime delta T epsilon. And in the case of non-oriented mean curvature flow, the problem consists simply to approximate SQ prime instead of SQ. So the problem is very similar for the oriented and non-oriented mean curvature flow. Okay, so just a little point about the database. I explained that I only know the theoretical evolution of circle, and this circle is given by a circle with radius satisfy this law. So I can pick a finite family of radius Ri and define the database where the incoming neural network is given by the fast field representation associated to the ball of radius Ri, and the outcoming of the neural network is associated to the same fast field representation, but where the new radius is given by the square root of Ri square minus 2 delta t. So, and so, where phi here is Q or Q prime, following the problem of oriented mean curvature flow and non-oriented mean curvature flow. And so we see here that, in fact, the semigroup SQ prime, for instance, if I apply SQ prime to xi, I obtain yi with this definition. So to optimize the parameter of the neural network, you minimize the L2 loss function, which is simply a L2 error on the database. And if you want to stabilize the optimization, you can also consider a multi-step L2 loss function, which consists not to look only at one time step, but many time steps. But it's help for the non-oriented case. And in practice, you use k equal to 5. And to minimize this kind of loss function, we use the PyTorch environment, and we consider an optimization with a mini-batch stochastic gradient descent with adaptive momentum, which corresponds to use Adam optimization algorithm. Okay, so now I just to specify the structure of the neural network. I recall that finally the semigroup SQ in the oriented case can be approximated by a scheme which derives to the discretization of the Allen-Cahn equation. And if I want to discretize the Allen-Cahn equation, using, for instance, this scheme, we see that UN plus 1 can be obtained by an operator applied to this function. And more precisely, this function can be seen that a reaction neuron applied to UN, just a 1D function. And this operator can be modeled by a kernel convolution with an operator. So your idea is to consider a neural network, S theta, which a combination of a diffusion operator, D, which corresponds to find the kernel K1, and to combine with a reaction neuron, which should be an approximation of a 1D function. So in practice, you need to introduce a discretization of your picture with, for instance, 2 height nodes. We fix also the value of epsilon and delta t. And then the idea is that a diffusion neuron is simply modeled by a discrete kernel where we adapt the size with respect to the choice of delta t and epsilon. In fact, you want to facilitate the training, so you should be interesting to have a kernel not so large. But if it's not so large, the risk is to obtain some anisotropic effect. So in practice, you choose the size of the length of the kernel given by 17. And if we plot the hit kernel in this kernel associated to delta t and delta x, we fix this value to have a good approximation of the hit kernel. The second point is about the reaction neuron, which is a 1D functional. And to approximate and to find a definition of Rho1, we propose to use a 1D multi-layer perceptron with 2 hidden layers with respectively 8 neurons in the first layer and 3 neurons in the second one. If you do this, here for the perceptron, we also use for the activation function a Gaussian functional to be sure that the function is sufficiently smooth. Which is not, for instance, the case if we use a ReLU activation function. And the first remark about this choice of neural network is that it's not so big because we have only 336 free parameters to optimize. So it's not too big with respect for the more classical neural network, for example, CNN or UNet. We have 1 million of degree of freedom. We can also consider some higher order neural network, and we are inspired from recent work with Elie, which propose to generalize the splitting method. And if you do this, in fact, if you apply this kind of scheme with m equal to 2, we can see that it corresponds to apply to consider this neural network where you only need to apply 2 diffusion neuron and 3 reaction neuron. And with this second order neural network, which is inspired by this kind of scheme, we have only 725 degree of freedom. So it's not also so big. Okay, so if now I come back to the motivation, which consists to learn the mean curvature flow, we first consider the approximation of the semigroup FQ, and we see that the algorithm optimization algorithm succeeds to minimize the loss function. And if you test the different scheme on the same initial set, the scheme which is given by the resolution of the Allen-Cahn equation, the first order neural network and the second one, we see that qualitatively the solutions are exactly the same. But now, if you want to observe a quantitative comparison, I can consider the evolution of the circle. And if I plot the error on the radius of the circle, which is known, we see that the scheme obtained with your neural network is better than the error obtained with the discretization of the Allen-Cahn equation. And this is in certain sense expected because the discretization of the Allen-Cahn equation with the splitting, first order splitting method is in the model of the first order neural method. So if we optimize all the parameters, you can find a better choice of a parameter which compensates the discrete error in t and time, and also an error in epsilon for the facile approximation, because here we consider the Allen-Cahn equation. It is interesting to test this neural network in a more general situation where we add some constraints. And so we consider a multifacement curvature flow here, where you simply replace the resolution of the Allen-Cahn equation by apply your neural network, which is in with only one phasis. And if you do this, we see that the resolution is, we see that the neural network can be applied in this context to obtain an approximation which seems to be very good. And we can also add here in this example some constant of volume, which shows that also that the trained network is stable enough to be associated with additional constraints. So your problem, in fact, here is to approximate the case of non-oriented mean curvature flow. So we do exactly the same. So now we consider the approximation of SQ prime. And if you do this, you see that the loss function decrease along the optimization process. But if you apply now the first order neural network, we see that we don't succeed to keep the cycle and to be evolved. However, the second one succeeds to do this. And if you plot now the law of the radius, you will see that it satisfies the good law. So this example shows that the second order neural network are able to approximate this kind of evolution in the non-orientable. And if now we want to compare an evolution in the orientable case and a non-oriented case with the same initial set, we see that the solution is very similar. We see that we have obtained a numeral scheme which can be exactly the same for the Allen-Cahn equation, but in the non-orientable case. And more precisely, if I look the algorithmic cost to apply this neural network, the second one, we see that we only need to use two differential to apply two kernel convolution, which can be done by using 4 fast Fourier transform. And so we can observe that this evolution have finally a cost twice as large as the semi-implicit of the Allen-Cahn equation. So the scheme has the same, in certain sense, the same simplicity. The interest is that now you can apply your neural network scheme where the initial condition admits some singularity. I recall here that in your learning base, we have only considered some evolution of circle and not interface with triple point. And so, which is very interesting, is that we observe that the triple point is appear to be stable and also satisfy the Jourdan condition, even if we don't help the neural network to satisfy this property. Okay, I just have an example of simulation with a lot of triple point, and you see the evolution we can obtain. So it's a very natural evolution. And if I come back to the Steiner problem, so we can just give an approximation by apply a non-logarithmic curvature flow through gamma with an additional inclusion constraint. We can be done in facile context by an inequality constraint. And so we obtain a natural numerical scheme to apply the neural network and then a projection of the inclusion. And if you do this, you see that the evolution converge very fast to the Steiner solution associated to the number of points. To conclude my talk, we also test in 3D. This is a numerical experiment here. And the new problem is to train a new neural network S theta in the 3D representation, where the database contains only the evolution of sphere and cylinder, which is also known. And if you do this, we can also obtain, with this kind of approximation, a scheme which optimize. This is an optimization of this is a simulation along the iteration, and you see that the interface, which is not oriented, converge to the solution of the Plateau problem. And we also put the Steiner solution of where we consider different value of the boundary. Okay, so I just finished my talk, and to conclude, we present here a general methodology to approximate many geometric flow. We only consider in this talk perimeter, but we test it with more flow and isotropic mean curvature flow, and it's work also in the oriented case and non-oriented case. So which is very interesting to have a simple scheme to be able to evolve by mean curvature flow this kind of situation. And also it's work also in arbitrary dimension and co-dimension. So it's very nice, and we expect that we can use it for many applications where involve non-oriented surfaces, as for instance the Montfort functional. And finally, the interest to have also a very simple neural network is that we expect to succeed to recourir geometric information about the neural network. And typically, if I consider the first order neural network, and I consider an evolution of anisotropic mean curvature flow, we have the first result. We explain how to find the anisotropic energy from the kernel, the diffusion kernel. And so it should be very interesting, for example, in application of nanowire, where we do not have real estimation of the anisotropic energy. So I just finished my talk, and thank you for your attention.
Thank you, Elie. Thank you for your talk. The floor is open to questions, and so feel free to either raise your hand or put a word in the chat box, and then we'll allow you to ask your question directly to Elie if you want, or we'll ask the questions ourselves. So please, so there is one hand raised. Let's see, I have to find who it is. Antonin, if you want to ask your question, go ahead.
Can I speak now?
Yes.
Yes. Thank you, Elie. I have a few questions, but I have one question on the last experiment. Two questions, actually. One, which is related to 2D or 3D, is when you say you enforce some boundary here, you say it's with this inequality, if I understand well. So what do? You alternate, you do your network, and then you enforce this inequality by just...
Yes, it is exactly the same for the Steiner problem. In fact, we assume that in fact U is lower than U in, and U in is it's a phase field representation of its nodes here. But for the 3D problem, we consider the...
Okay, that's what. Okay, I had missed the inequality.
Yes, there is not the sum. It's a wrong mistake.
No, it was on the other side. But then this does not create very singular things that it still works afterwards when you pass through the network. So okay.
Yes, because in fact this is smooth. In fact, this function is smooth. And this function is also smooth, and so this is also the interest of the phase field. This is exactly the same for the problem of 3D segmentation problem with slice. We have constraints which are smooth, since the function is smooth.
Okay, and on the 3D specifically, when you train, what kind of training do you have? Because there are a lot of possibilities for a surface to evolve.
We consider only sphere. Well, at the beginning, we consider only sphere. It's work, but it was surprising. And then, as you consider the system with periodic boundary condition, we consider an evolution of cylinder with periodic boundary condition. So we consider only exact evolution of mean curvature flow,
But did you check? It's very strange. Did you check that the result have more or less zero curvature? How does it know when something has zero curvature if it's trained only on spheres?
No, we don't test it because but we have other technique, and we know that is near the solution of the Plateau problem, because a very different technique gives us the same kind of solution. Okay. So but we don't test in practice the computation of the curvature. In fact, it is also sorry.
No, I mean the network never really learns what is a zero curvature.
No, it's never learned. Here it learns only the semi-group which consists to evolve at the time t and time t plus dt. Yeah, sure. Okay, so we apply a lot of times the neural network to obtain this kind of iteration. I think we see here the number of iteration when you apply a lot of iteration, but one neural network, when you apply the neural network, we only need to apply 4 Fourier transforms, so it's not so long.
Sure. Okay. Well, thank you.
Thank you, Antonin. Please, if you have other comments or questions, don't hesitate to manifest yourself. In the meanwhile, Elie, I had a question about, you presented 2 types of networks, which you called first and second order. Can you give us more detail about that, in the sense that what makes them first or second order? And it is order with respect to what?
In fact, the first neural network is just application of a 1D function and then a kernel operator. Mm-hmm. If you consider this neural network, we see that we don't succeed to learn to reproduce the semi-group associated to Q prime, the non-oriented case. And in fact, we also, at the beginning, if you consider only oriented case, we know that we can obtain an approximation of the semi-group with an error in delta t and delta x square, because this is a classical error given by this scheme, and this scheme is an example of this neural network. Right. And the problem is that if you want to obtain a best precision in delta t and delta x, you need to introduce height order semi-implicit scheme. So to obtain better precision in time and in with respect to the discretization in time and in the spatial variable, we apply we look the form of height order semi-implicit scheme, and here in fact E1 is associated to the diffusion operator, and E2 is associated to a nonlinear functional.
All right.
And so we consider this plan, and you see that, for example, if I apply this plan, the first iterate, U1 is the outcoming of the first neural network. But now you can also combine with other information in U0 and U1 to obtain E2. And you can use this procedure to obtain a more complex architecture of your neural network. And we expect that at least if you solve the Allen-Cahn equation, this neural network should be better than the first one. It is expected, and this is what you observed for the Allen-Cahn equation. But the problem is that with a complex structure of the neural network, we have a number more important of parameters to optimize, and so it's not clear if you use a too large neural network to be succeed to optimize the problem. So this is why we introduced it, and which was surprising is that it worked for in this situation. It was a surprise. You test and it worked, but at the beginning we consider this architecture to be more precise than using only one diffusion and one reaction.
All right, but you don't have a theory that says, well, you could develop neural networks for the 1, 2, 3, 4, whatever.
No, but I know that if I want to learn the Allen-Cahn equation, I know that with this neural network, I can do better than this scheme, which is an error in delta t square. Okay, so I know that here we have an error in delta t square with capital M equal to 2. Then using this, we know that we cannot do better than an error in delta t. So in certain sense, using, for instance, this neural network should be interesting if you want to use larger delta t.
I see.
Estimation of delta t. So so we can be interesting. And if I consider now a third version, because in the preprint you put a third version of a further neural network, you can estimate that you can use this kernel with a little delta t, or this neural network with a more larger delta t. But it's not clear. We cannot say anything. We can say just one thing about the Allen-Cahn equation. We can say anything about this function. For example, if I consider the Wilmore flow, I know that it's impossible to learn the Wilmore flow with this kind of neural network, but it should be possible with this kernel, I believe, because the discretization of the approximation flow of the Wilmore flow need more than one diffusion operator, and one to apply a diffusion operator to a reaction operator. So you need to have a more complex neural network.
So presumably, if you have an idea of how to write a numerical scheme for the Allen-Cahn equation or the equivalent equation for the Wilmore flow, that should give you a guideline to build for the structure of the neural network.
Yes.
Okay. Thank you. Are there any other comments or questions? Mauricio, you're allowed to talk.
Thank you very much. Good afternoon, and thank you for the interesting presentation. I have a couple of curiosities and questions. So the first one, I understand that intuitively, if you have a scheme that is order 1 and that represents a good approximation of the semi-group, then you improve the accuracy of the procedure. But I don't understand how you couple this information with the construction of the neural network. So I mean, you start with something which is order 1, and then you have to construct a neural network, hopefully obtaining a result which could be at most order 1. But what are the rules that you apply in order to construct the network? Is there any theoretical result behind this? It's just a heuristic? It's based on your experience? Is what? I mean, I don't understand how far is going the theory in this direction.
In fact, at the beginning of this work, we only consider the Allen-Cahn equation. And the Allen-Cahn equation, we have a lot of numerical scheme which can be. Okay, I prefer to show you this this example. The Allen-Cahn equation with this scheme. Okay, in this scheme we have a regularization parameter alpha, and so we see that this alpha should modify the estimation of the diffusion kernel and the reaction operator. And so, in fact, at the beginning, we only try to optimize alpha and also the kernel associated to a diffusion operator. And then we see that it was not sufficiently large, and we see that the reaction operator can be optimized with one function. At the beginning, we want to see that one is a typical form which depends of the double well potential, W. So we consider a very little class for ρ1, but you consider 3 kernel for the diffusion operator. The first experience consists to show if you can approximate anisotropic mean curvature flow and to build some anisotropic kernel to fit with an anisotropic law. So we fixed the value of the function 1D, and then we have the idea to free this form by observing that it's only a 1D function, and so we introduce an approximation of a 1D function, which is classically well done by using a perceptron. So at the beginning, we obtain the neural network DR. First, by want to optimize the kernel, and then by optimize in the same time the kernel and the reaction operator. This is not in PyTorch, this is in MATLAB. And then when you consider this kernel, we use PyTorch, but at the beginning we do all the experiment in MATLAB with a classic technique. And then we focus on the Camille and the Wilmore energy. And we saw that in the Wilmore energy, it's in certain sense the derivation of the Allen-Cahn equation. So you need to, and we also inspire your neural network from a Bench-Merriman-Osher algorithm for the Wilmore flow, which alternate, in fact, which consists to take this neural network in parallel with another one, and then to combine with a last example. So we inspire your neural network from classical scheme, Bench-Merriman-Osher, discretization of the Allen-Cahn equation. And then we observe that this neural network is in a typical form of this one. And so we now have an idea how to generalize it. But this is, in certain sense, heuristic. And as soon as this neural network succeeds to approximate the case of non-oriented mean curvature flow, we consider that it's very good. But we know that it is not enough to approximate Wilmore flow. So now we consider a third-order neural network to expect to approximate Wilmore flow. So it's depends on of the law, but this is in certain sense heuristic. Also.
Thank you.
So I don't know if I.
Well, okay, it's a partial answer to my question. And just a curiosity, how long it takes the training part?
We can observe that the number of parameters is not so long. So it's about 4 hours in certain time. We don't know, because when you see the when you observe the loss function, you see that if you take 4 hours to do this, we can stop here, in fact. So it's not clear when you can stop, but it's not so long because the number here is not so large. And also, I don't say, but the number of database, I believe, I'm not sure, but I believe we consider only 100 different circles, so it's not so big.
Okay, thanks.
Yes.
Thank you, Mauricio. Any more questions or comments? Well, if not, thank you, Elie, again for your talk. It was very interesting. And thank you all for attending.